Today, we want to continue solving equations with this particular technique where we read the expression and then do inverse operations in reverse order. This is very calculator based and we're going after approximations, but we want to reinforce our ability to read an expression and make a plan based on that reading. So let's look at an example. I'm going to set up two equations that will look very similar because they'll use the same three operations, but the parentheses will put these operations in a different order. So for example, let's see, something that we haven't used for a while. 2 times x minus 5, then cubed. More like 2 times the cube of the difference between x and 5. And let's suppose that we'll put this in an equation. Let's suppose that this is equal to 11. I was using 10 yesterday, so it's time to use 11 today. What we want to do is identify the three operations and the order that they happen to turn an x into an 11. So we're going to turn x, this equation says turn x into 11 by doing these things to it. First, take the x and subtract 5. Second, raise to the third power. And third, multiply by 2. So this informs us what we should do to solve the equation. If we want to take an 11 and turn it back into x to figure out where the 11 came from, first, we're going to divide by 2. Second, we're going to raise to the 1/3 power. The inverse of an exponent is a reciprocal exponent. And third, we will add 5. The inverse of subtraction is addition. The inverse of multiplication is division. So here are inverse operations in reverse order. So here we are reading the expression. And then here we are going to do inverse operations in reverse order. We're going to start with 11 and we're going to perform those three operations. So we're going to start with 11 and we'll divide by 2. I'm just going to do the whole thing on a calculator because this is stuff that we're typing into the calculator. Remember, these first two steps are things that are going on in our mind. So we're just thinking these things. Then here's where we're going to do the calculator stuff. We're going to go 11 divided by 2 is 5.5. We're not writing this down. It's just showing up on the calculator. And then we'll take 5.5 and raise that to the 1/3 power. So take 5.5 and just hit raise to the parentheses 1 divided by 3. Don't forget your parentheses around your fractions. And we get 1.765. We're not writing this down. I'm just making a note of what's happening on the calculator. And then we'll take the 1.765 and we'll add 5 and we'll get 6.765. Can take place totally in the calculator environment. What we'll actually write down on the page is x equals 6.765. Mostly because I usually ask you to round to the nearest thousandth. So once again, from a writing standpoint, these first two columns, we're reading the expression in inverse operations in reverse order. This is taking place just thinking. We're thinking this part. So this is just taking place in our mind. This part is all taking place on a calculator where we actually perform the operations. This is just us punching numbers into our calculating machine. So that's the calculator stuff. And this is the answer that we actually write down. The goal is to read the expression and come up with our plan to perform inverse operations in reverse order, and then ask a calculator what those numbers are. Let me write another equation involving the same three operations, but in a different order. Let's say the 2, instead of being outside the cube, was inside the cube. Let's suppose that we had 2x minus 5 cubed equals 11. That's not what I wrote. The cube of the difference between 2 times a number and 5 is 11. This equation uses the same three operations. There's multiplication by 2, there's subtracting of 5, and there's a raising to the third power. But it does them in a different order. This is how we read the expression over here. To turn x into 11, first, we multiply by 2. Second, we subtract 5. And third, we raise to the third power. So our plan for solving is to perform inverse operations in reverse order. So we'll start with 11, and first, we'll raise to a 1/3 power. The inverse of an exponent is a reciprocal exponent. Second, we'll add 5. The inverse of subtraction is addition. And third, we'll divide by 2, because the inverse of multiplication is division. This is all just what we're thinking. On our calculating machines, we'll start with 11, and we'll raise it to the 1/3 power. So 11 to the 1/3, make sure you use parentheses around your fractions, and we get 2.224. We'll round that off, even though we're not going to round it off in practice. Then we'll take the 2.224 and we'll add 5 and get 7.224. And then we'll divide by 2 and get 3.612. And then we'll report our answer, x equals 3.612. Any questions? So once we start, if we start writing this down, this is where we can begin. We can begin by writing all this down, but the goal is to just think these two columns, use our calculator for this last column, and write down the answer. That's the goal. That's what I want it to look like. While this is happening, we can discover some things about how we write things. Notice that the first thing we did here is raise to a 1/3 power. And this is kind of cumbersome, so we can start to understand why we didn't want to use fraction exponents back in the day. It's like, well, let's come up with notation for this 1/3 power. And let's call that the cube roots of 11. And then now we have a much more portable form for 11 to the 1/3 power. This is possibly one of the reasons that radicals exist. I always say we did this, but I wasn't there when when this notation was invented. Let's suppose that we didn't have calculators because it's back in the day and we don't know what the cube root of 11 is. That would be embarrassing back in the day, I think. If you're like a mathematician, you should just be carrying stuff like this around. I don't know. I don't know what it was like back then. But let's suppose we have the cube root of 11, whatever that is. We know it's between 2 and 3 and probably closer to 2, but whatever that number is, we can worry about that later. And then what we're going to do is we're going to take the cube root of 11 and then we'll add 5 to it. And then the last thing we're going to do is take this whole result and divide it by 2. So we can write the cube root of 11 plus 5. And I want to divide by 2, but I want this addition to go before this division. So I'm going to use parentheses. We could say that this is the exact value of the 3.612. This is an approximation to the nearest thousandth. This is the exact value of the solution. And then the 3.612 is an approximate solution. Rounded to the nearest thousandth. So this is another fun thing to practice. Write down what the exact solution should be. So and this will help us understand the order of operations better. So if we think about the exact solution in the first example, if we take the 11 and we'll divide that by 2, and then we want to raise this result to the 1/3 power, or take the cube root of the 11 divided by 2. Make sure my radical bar goes over the whole fraction. And then the last step is to take the cube roots of 11 over 2 and add 5 to it. And so here would be the exact solution in the previous problem, where here we have the approximation. At this point in the process, I'm going to be asking for approximations to the nearest thousandth. But there could come a time in the future, and I don't know when this time is. It may never happen. Then I'm going to ask you for a favor. Wait, no, that's different. That I'll ask for the exact solutions. So if we're looking for exact solutions, then this is what we'll have to write. You can also write it in the full-on tall fraction format. If you're like, well, I like to use tall fraction format. Which is fine. Because now you're using the fraction bar as a grouping symbol rather than parentheses as a grouping symbol. Any questions? All right. Now, you must be thinking that this can't be it. There has to be something else. And so, of course, there is. One of the important things that we recognized that's kind of a new information is that the inverse of an exponent is a reciprocal exponent. So the inverse of an exponent is a reciprocal exponent. I don't want to say fraction exponent, I want to say reciprocal exponent, because it's possible to start with a fraction exponent because it's possible to start with a radical. So let's look at an example like that. Let's look at an example of an equation with a radical in it. In case you haven't noticed already, today is going to be death by examples. So let's suppose that instead of raising the 2x minus 5 to the third power, let's suppose our equation had the cube roots of 2x minus 5 is equal to 11 is fine. It's going to make big numbers, but that's fine. So this is a completely different kind of equation. Instead of a polynomial equation, we've now got a radical equation, and it is pretty rad. Let's look at what happens to turn an x into 11 in this one. So how does x become 11 in this equation? First thing that happens is we take the x and we multiply by 2. Then the second thing that happens is we subtract 5, because multiplication goes before subtraction unless there are parentheses between the multiplication and the subtraction. So second, subtract 5. And third, we do a cube root of the result. What we want to notice about the cube root is that the cube root is a 1/3 power. So now we're going to move into phase 2. We've read the expression. Now we have to come up with a plan for turning an 11 back into x. We've got to invert this process. first, we're going to undo the cube roots, or a 1/3 power, with a reciprocal exponent. The reciprocal of 1/3 is 3. So we're going to raise this to the 3rd power. The reciprocal of 1/3 is 3. Next, we'll add 5 because that's the inverse of subtracting 5. And finally, we'll divide by 2 because that's the inverse of multiplying by 2. We have now come up with a plan. We've read the expression, and now we're going to perform inverse operations in reverse order. We're going to grab our calculator, and we're going to say, hey, calculator, what is 11 to the 3rd power? And our calculator is not going to say anything because it's a typing thing, not a speaking thing. We raise 11 to the 3rd power, and we get 1,331. Then we take the 1,331 and we add 5 to it. And then we're going to take the 1,336 and divide it by 2 and come up with 668. Oops. And then we will report our answer and say X is equal to 668. This one is not approximate. So that is a great observation. We don't need to round it to the nearest thousandth because we did not get an irrational answer. So that's a good thing to watch out for, because my instructions are going to say, show your calculations, round your answer to the nearest thousandth if it is irrational. In this case, it's not irrational, so we need not round it to the nearest thousandth. We can just write down the exact value. One thing I've been forgetting to do today is to check. So we should do that. I should take the 668. I should take 2 times 668 is 1336. And then take the 1336 and subtract 5, and that's 1331. And then take the cube roots of 1331, and that's 11. So everything checks out. Oh, we should always check our answers. This is what the problem hinges on: reading radicals as fraction exponents and knowing that the inverse of an exponent is a reciprocal exponent. How's everybody okay? Cool, we can dig it. We do just have to be careful about how we read our equations. So I'm going to flip this around a little bit again. I'm going to say, what if we have the equation that says 2 times the cube roots of x minus 5? This is just the radical version of the problem on the previous page. Once again, this is happening in our mind, but first we're subtracting 5. Second, in this case, we do the cube root, which is a 1/3 power, and then we multiply by 2. We flipped around the multiplying by 2 and the cube roots. We've changed their place in the order of the operations. So our plan for solving, we'll turn 11 back into x by first dividing by 2, second raising to the 3rd power because the reciprocal of 1/3 is still 3, and third we will add 5. Grab our calculating machine. 11 divided by 2 is still 5.5. 11 divided by 2 is still 5.5. 5.5 to the 3rd power is 166.375. And then 166.375 plus 5 is 171 0.375. And that's what we'll report as an answer. This one is also not an approximation, because if I say to the nearest thousandth, the whole number goes to the nearest thousandth anyway. This number is also not irrational. It just happens to stop at the thousandth. So this one is also exact. Notice that we can convert this one to a fraction. We'll be able, yeah, 1371 over 8. We can write this as a fraction. 0.375 is 3/8. So this is 1371 over 8. If we subtract the 171, there's our fraction, 3/8. So it's not irrational because we can write it as a fraction. And as usual, we should check. Oops, put the 171 back. As usual, we should check. So we'll take the 171.375. And we will do these steps to it. First, we'll subtract 5. Is the 166. And oops, dropped off the scene. There's the 166 at 0.375. Take the 166.375 and take the cube root of that. I'm going to use a 1/3 power, and then we'll get 11 over 2. And then take the 11 over 2 and multiply by 2 and come up with 11. So everything checks out again. We should always check our answers because that way we will always know that we're right. If we didn't get 11 after running it back through the process, then we know our answer is incorrect and we have to go back and fix it. That's why solving equations is such a good thing to practice on, because we can check our answers. We don't need the back of the book. We can just check to see that our answer is right. And if we get it wrong, we get to go back and fix it. Any questions? So the first big thing that we encountered when we started solving equations by performing inverse operations in reverse order is that the inverse of an exponent is a reciprocal exponent. The inverse of an exponent is a reciprocal exponent. Here is one bit of a wrench in the system, something that we have to remember. And here's the way I phrase it. Even exponents do not respect negatives. Even exponents don't respect negatives. That is to say, even exponents turn negatives positive. Even exponents are that friend that are always like, oh, hey man, just cheer up, as if that's how depression works, right? So, dude, that's not how it works. That's not how emotions work. You don't just decide to have the emotion. It's like when someone's angry, you can't just be like, oh, calm down. It's like, well, that's not how angry works. Otherwise, there wouldn't be things like fights. Someone would get angry and someone would go, hang on, I got this. Calm down. And they're like, oh, whoo, thanks, man. I was angry, but you said calm down. And so that fixed everything. It's totally the opposite. If someone is angry and you tell them to calm down, that's just going to make them more angry. Saying things like calm down and don't worry or cheer up, these are all just things that that demonstrate how badly we understand emotions. That's not how it works. Anyway, I mean, sometimes sad is a perfectly valid thing to feel. I don't know why we all got to cheer up all the time. And I don't know if is this an American thing? I don't know. Yeah, so that it makes you feel bad for seeming different, and also that it's wrong. It makes you feel wrong for being sad. It makes you feel that there's something wrong with you, and there's nothing wrong with you. It might be perfectly natural to be sad. Sometimes you're just sad. Don't feel bad about that on top of being sad. You know what I mean? It's perfectly normal to be angry. What's not normal is to punch things because of it. The emotion is what we need to learn about. Our behavior is something that we need, is what we need to learn how to, is what we can learn to control. We can learn to control our behavior so that we can deal with our emotions better. I know this is just a math class, but it really bugs me that negative times a negative becomes a positive, because, you know, that's just not how things work. Also, in English, a double negative will cancel out, but not in every language. Like, I grew up thinking I'm not going to the store. Oh, two negatives make a positive. I am going to the store. But not in every language. And even some English phrases, we don't cancel things out with a double negative. And it should be really obvious that that happens, because I don't know if this is just a California thing, but if the answer is no, how often do we say, yeah, no? But if the answer is yes, you're like, oh, no, yeah. It's like, oh, wait, what? That's like, which one is it? Is it a California thing? I spend too much time in California, so maybe that's a California thing. I don't travel enough. Yeah, no, I don't travel enough. It's like when your friends are watching TV and you want to change channel, and it's like, oh, can I change a channel? Do you mind? I'm like, oh, dude, you just asked two questions, and I have to make sure I get the order right, because now there's like a yeah, no, or a no, yeah. So I always have to wonder about where the thing. I always try to think about where the things that I say kind of commonly. Is it a United States thing? Is it a California thing? Is it a Bay Area thing? Or is it a coastal thing? Because I grew up in like Moss Beach, Montera. So maybe it's like really that, if it's that specific. I know in England, if you listen to someone talk and they're not putting on a voice, you can kind of like almost nail down the village they came from. I don't know if that's true in California, I think, or in the United States. I think you can go for regional things, but you can't nail it down. It's like, oh, it's not like you're from California. It's like you're from the Bay Area. And it's not just you're from the Bay Area, you're from specifically San Francisco. I don't know if you can do that. What are we talking about? Oh, yeah. Even exponents don't respect negatives. Even exponents make negatives positive. So what this means for us is that if we have an equation where x is being raised to an even exponent, if you have x being raised to an even exponent, you're going to end up with two solutions. So if we're solving in equations, so I didn't have Mr. Evans for band. I didn't go to Half Moon Bay High. So equations with even exponents, this is the implication, is what we need. Equations with even exponents will have two solutions. So here's an extra thing that we have to remember. Equations with even exponents will have two solutions. For example, let's start with the most basic example. If we want to solve x squared is equal to 4, there are two values of x that make this true. X equals 2 and x equals -2. We have two solutions. 2 squared is 4, and -2 in parentheses squared is 4. Even exponents, equations with even exponents will have two solutions. They won't always just be opposites, but will always have two. So for another example, if I have x to the 6th is equal to 12, there's only one operation here. It was raised to, x was raised to the 6th power. So the inverse operation is a 1/6 power. Oops, I spelled 6 wrong. That's not good. It's going in this direction. The inverse operations in reverse order is a 1/6 power. So I'm going to take a 12 to the 1/6. And here's where we get the two solutions. So I need to know 12 to the 1/6 power, 1.513. But even exponents will make two solutions, and when we do the reciprocal exponent, that's when the other one shows up, and also -1.513. So there was an even exponent, so I should expect two solutions. X is 1.513, and x is -1.513. Any questions? All right. So for more Leach cosine facts, I did go to Cunha Intermediate, and so I had Mr. Smith for orchestra. So I played trombone in the orchestra. But then after Cunha, at the time, I don't know if it's still true, but Half Moon Bay did not have a swim team, and I was a swimmer, and so that's why I went to Sarah High School so I could be on the swim team. So more facts about Leach you didn't need to know. All right. So the two solutions are not always going to be negatives. It depends on when the two solutions show up. So one last example. I think I could squeeze it in and not switch pages. Let's suppose that I have x minus 4 to the 6th is equal to 12. So x minus 6 to this x minus 4 all to the 6, or say the 6th power of the difference between a number and 4 is 12. So the things that happen to x, first we subtract 4, and second we raise to the 6th power. That's going forward. That's reading the expression. Inverse operations in reverse order. First, we'll raise to the 1/6 power. This is where the two solutions will show up. And so moving forward, or backward, when we add 4, we're going to have to add 4 to each one. So when we undo an even exponent, this is where we make two solutions. This is where they split when we undo the even exponent. And so we will have to add 4 to both of the solutions. So that's where the two solutions show up, when we undo the even exponent. So solving this equation on our calculating machine, we're going to start with a 12 to the 1/6 power, and we'll have a plus 1.513 and a negative 1.513. So we have to add 4 to each of those. So we have to do it separately. So we'll first add 4 and get 5.513. That will be one of our solutions. And our other solution will start with a negative. So I'm going to go back to the 12 to the 1/6. If I make that negative, and then add the 4 to that one, I'll have 2.487. And that will be our other solution. So equations with even exponents will have 2 solutions. If we really want to be specific about things, right now your challenge is just to deal with the inverse operations in reverse order. I've added one layer to that. If I start off with an even exponent, x squared, x to the 4th, x to the 6th, or something like that, then we're going to end up with 2 solutions. Notice just even exponents. 1/2 is not an even exponent. It's when the equation itself has an even exponent, an even integer for an exponent. That's when we're going to end up with 2 solutions. Just to clarify, we'll have 2 real solutions. If you really want to get into the weeds, think about why I have to add that qualifier. 2 real solutions. Any questions? Cool. Hey, fellow swimmers. I was a swimmer in high school. My events were breaststroke and individual medley. Individual medley was a lot of fun because my backstroke was utterly horrible. This backstroke was my slowest stroke. It was just the worst. But I was a breaststroker, so I was a negative split IMer. So I was always a come from behind IMer. So I go out, I could keep up in butterfly. Backstroke is where I just got toasted, and then I had to make it up. I always had to come from behind and try to make it up on the breaststroke lap, and then try to hold my own on freestyle. My freestyle was pretty weak, but breaststroke was pretty good. It was all legs. When we did kicking exercises, so like a kicking set, if it was a breaststroke kick, it was a whip kick set, it was almost as fast as I could swim breaststroke. So, and I'm paying for it now because my knees are trash. Anyway, what are we talking about? Anyway, swimming. And now I think if you threw me in a pool, I would probably drown. Anyway, that's the new thing. Even equations with even exponents are going to have 2 solutions. The first quiz on solving equations is not going to involve this. It's just all going to be variations of ×2, -5, and to the 3rd power. But then subsequent quizzes are going to start throwing in these variations that we're talking about, like radical equations. I want you to be able to read the expression, come up with a plan by performing inverse operations in reverse order, use your calculating machine to perform those inverse operations in reverse order, and just write down your answers to the nearest 1,000th. Now that's going to do it for today. I'll see y'all tomorrow. Everybody have a good day, and thanks for playing.